Okay, hi DiffyQs, how are you? Let's go over some homework first before we get to new content for today. And looked at these 4 questions that I assigned, and I'm guessing that 19 and 35 are the ones that probably had some questions, okay? So let's just walk through what I did here. So here's the original DiffyQ. I put this into standard form by dividing everything by x plus 1, and I just saw here that I forgot to have an x plus 1 down here. Goodness. Okay, then I found the integrating factor. So the integrating factor is e to the improper integral of this. The integrand here is an improper rational function. A little bit of a refresher here. An improper rational function is a rational expression, I'd say. It's not a function. An improper rational expression is one where the degree of the numerator is greater than or equal to the degree of the denominator. I lost the equal sign my first time through. And when you have an improper rational function as an integrand of an indefinite integral, a very helpful and commonly used technique is polynomial or synthetic division. I'm just going to do long division here. I'm going to do x plus 2 divided by x plus 1. I did the division right here. Notice there is a remainder. So x plus 2 divided by x plus 1 equals 1 plus 1 over x plus 1, right? Because it's 1 plus the remainder here divided by the divisor. So, okay. And now what I've done is I've rewritten the improper rational expression as a sum of simpler rational expressions, so to speak. And I can now take that indefinite integral, and here is where I am. Okay, and then what I'm going to do is multiply the DiffyQ by x plus the natural log of x plus 1. And when I do that, x plus the natural log of x plus 1, I get here. Okay, when you multiply all of that, x plus, sorry. I first have to remember this is I beg your pardon, e to the x plus the natural log of x plus 1, okay? Then here's some algebra, properties of exponents. E to the x plus natural log of x plus 1 is the same thing as e times e to the x times e to the ln of x plus 1, and e to the ln of x plus 1 is just x plus 1. And then what we're going to do here is multiply all of the terms in the DiffyQ on the left and right hand side by e to the x times x plus 1. And I just realized that I have to adjust because of my mistake up here. Do you see how when I divided by x plus 1, I didn't keep that here? You know what I mean? So let me just fix that. Hang on a second. Okay, I'm back. So here, where am I? So when you're here, so notice after multiplying by e to the x times x plus 1, we get this DiffyQ here in green. And you know that the left-hand side is always going to be the derivative of the integrating factor times y. And some of you may be looking at this and looking above and saying, like, how does that happen? So I just said, if you feel like checking, you can certainly go over here and check it out. And you'll see fairly quickly here that, oh, it actually works out beautifully, okay? Notice here on the right-hand side, simplify the e to the negative x times e to the x. So the right-hand side is 2x. After integrating, we get e to the x times x plus 1 times y equals x squared plus c. And then here is my final solution to the DiffyQ. The question about the intervals of definition, so let's talk about this. If you look at this solution right here, x can't equal -1. But everything else, I mean, otherwise x is fine. So really, there are 2 intervals of definition. Negative infinity to -1 not inclusive, or -1 not inclusive to positive infinity. This question asks you for the larger interval. And I know this is going to be a very wacky idea for some of you, but this is considered the larger interval, even though they're both infinitely large, okay? But there is something legitimate in math about comparative infinities, namely that not all infinities are created equal. So this is one case where it is not. So this would be the interval of definition, okay? All right, let's go to now 35, and 35, let's see, here it is, 35. Okay. 35 says, and I was going to do 45, but I think it's fairly straightforward now that I looked at it. So 35 says, here is some p of x, some function, it's a piecewise defined function. And you're asked to, I think, solve this differential equation where p of x is taking the place of this function of x right here, and given this initial value y of 0 equals 3. So there are really, in this question, two differential equations. So in the left-hand side here, you'll see that I have p of x equaling 2. On the right-hand side, you'll see that I have p of x equaling the other piece of the piecewise defined function, negative 2 over x. Okay, now here's where I just kind of work through. You can probably follow my steps here. This is the integrating factor. This then becomes the diff EQ expressed as a derivative of products on one side. This is now the integral of the right-hand side, which requires integration by parts, and specifically this breakdown. And then if you take that right-hand side all the way, okay, here's uv minus the integral of v du, and then take care of this integral here. At the end of the day, we get this family of solutions. 4 equals c, I got that using the point y of 0 equals 3. And the reason why reason why we input in x equals 0 and y equals 3 into this differential equation solution is because, don't forget, x equals 0 corresponds to this piece of the piecewise. Okay, then here's the other piece of p of x. So here is p of x. Here is e raised to the indefinite integral of negative 2 over x, right? And all I did here was algebraically clean this up. Properties of logs, negative 2 ln x means ln x to the negative second, which at the end of the day simplifies to x to the negative second. You then, multiply the diff EQ by the integrating factor, expressed on the left-hand side as the derivative of a product. Integrate the right-hand side here, and we get this function y equals 4x squared ln x plus cx squared. Okay, now here's the thing that's very peculiar to me. So this one, I was saying, well, how do I find c? And I made a little note to myself as I was thinking through it. I said, you know, I'm thinking about the relationship between different family of solutions. And so what I thought to myself was, in the original piecewise defined function here that was given to you in the text, do you see that? When x equals 0, y equals 2. And so my thought process was, x equals 0, y equals 2 became 0, 3. So I thought to myself, maybe I'm moving up 1. So I need to think of a point on the other piece of the function, so to speak. So I thought about the value of x equaling 2. When x equals 2, y equals negative 1. So I thought, well, let's think about when x equals 2, y equals 0. And then I used this point to input in to solve for this constant c. And for some reason, my constant c, for some reason, it's not matching up, because I did go back and just peeked. This is the constant c that your back of your book has, and I don't know how on earth they got that. So I'm a little bit flummoxed on how they got that c, because I think my rationale here makes complete sense. You know what I mean? But anyway, I'm going to give that some more thought and we'll get back to it. But let's finish the problem. So at the end of the day, p of x is, there's the top piece and here's a second piece. 4x squared ln x plus some constant x for values of x bigger than 1. Okay, and I think if I'm looking at this here, I think, you know, you probably could divide all the terms here by e to the 2x on the top one if you want to, but no need. All right, so on to the lesson for the day. Why don't you go ahead now and take out those notes. Remember when I changed gears, I did the that brand new method of integration first, and I said, let's just do do that more difficult lesson together. And then this one is largely a review, but I think, it's a review for some of you, but then for some of you, it's also new. Just integration methods reviewed. I'll talk about autonomous differential equations. And I know this will be a review for you also. And autonomous differential equations are kind of neat. They give you another way of visualizing solutions to diffie-Qs. Okay, so not that I necessarily wanted you to look at my solution here, but I gave you a diffie-Q and I told you to integrate by parts, okay? And integrating by parts requires, well, you know what you can do? Why don't you all try and just pause me here and try and do it on your own. Try it. Try and do it on your own. When you're ready, hit play. So integration by parts, what we're going to do is first, here we go. First separate correctly. And when you separate, that dingling, I'm so sorry. When you separate correctly, this is what we've got. Okay. And then what I did was I am looking at what's going on here. I don't understand. Okay, here we go. All right. When you separate the variables, we are here. Now look at the right-hand side. When you integrate the right-hand side, that's going to require, this is the left-hand side, so sorry. When you integrate the left-hand side, that's going to require integration by parts. And the right-hand side, look what happens. You have an improper rational function again, but not all improper rational functions require a re-expression by long division or synthetic division. And in fact, this one, look what you can do, a slick little trick. Divide each term by y. Not even a trick. This is like the first thing the first slick thing you learn when you started integration. And you're here comes the antiderivative, and this is my family of solutions. Absolutely impossible to solve for y. That's the family of solutions. Okay? All right. This one, just something for you to try. So one of the things that you learned in math, let's see, would that be math 2? It'd be TFA, is a method of factoring called factoring by grouping. And here's a differential equation where if you look at this in the original state, so look at the diffie-Q as it's given to you, hopefully you see there is no possible way to separate variables. It's impossible. But then if you kind of take a look at the top here for a minute, and if you try factoring by grouping, look what happens. And look what happens. And the denominator, look what happens. And look what happens. And then what you have here is a separable diffie-Q, and here is the separation of variables. Okay, now in this case we have again improper rational functions. Unfortunately, because the denominator is not just a monomial or a one term, you can't do the little trick up here. But what you can do is practice the skill that I just showed you that may have stumped you on last night's homework, which involved doing some long division to rewrite each of these integrands and then solving. Go ahead and try that together and then just kind of reconvene and talk out what you did. Okay? Okay, here is a nice one. And I know you should have about a full page below this question because it is going to take some work. I'm probably going to just scroll to the right. So here's an initial value problem, and hopefully you all take a look at this and see it as separable, and you have this. I want you to go ahead and solve for the particular solution, and then I want you to give great thought to finding the interval of definition. In this case here, determining the interval of definition is going to require great attention to the detail of the solution. So for example, you may be called upon to think about things like, I don't know, if there's a quadratic perhaps in the denominator, trying to figure out when that quadratic equals 0, you may find yourself having to use the quadratic formula, okay? So go ahead and try that with someone around you or on your own, and then consult and then replay me for the full workup. Okay, hello. So I think you all got to this point fairly comfortably. So the interval of definition, you need to determine where or what values of x will make this allow this solution to be differentiable and continuous, right? Although saying continuous is superfluous. So the radicand needs to be greater than or equal to 0. So the way I went about this was determining first when the radicand would equal 0. And because the radicand is quadratic, we're using the quadratic formula here, and the radicand would equal 0 at -1 plus or minus root 5 all over 2. So that gives you then 3 intervals over which you can talk about the radicand. And you'll notice that for values of x between -1 plus radical 5 over 2 and -1 minus radical 2, actually, I may have said those two backwards. Sorry, -1 minus radical 5 over 2 to -1 plus radical 5 over 2. Over that interval, the radicand is going to be negative. That leaves you with 2 possible intervals of definition. This one and this one. If this were not an initial value problem where we were not given a point, either of these would be fine. Either of these would be viable intervals of definition. However, we were told the given point is x equals -2. And the interval of definition that includes that given point is right here. So this would be the interval of definition. Okay? All right, let's resume. Let's go back to our notes here. What's interesting about differential equations, and we're going to obviously spend a great deal of time talking about these, is there are tremendous advantages when your differential equations are only in terms of the independent variable. And that's the world you lived in for much of your time through your tour of integral calculus in AB or BC. What I'm talking about, if we want to use y and x just as a shorthand here, the differential equations you really dealt with most of the time looked something like this, where the differential equation is entirely in terms of just the independent variable. Those are the easiest because you know that to find y, it is just a matter of integrating this expression with respect to x. But I want to make you realize also that these simple differential equations you did before you even called them differential equations are also separable Diffie-Qs. I mean, there's nothing that prevents us from really thinking about this differential equation as a separable differential equation by doing this and then just, integrating both sides the way we do. And we would get y equals the antiderivative of the right-hand side. So really, we've been dealing with separable differential equations for quite some time before you were even introduced to what the phrase meant. The point being here is Diffie-Qs probably are in its simplest state when we are just in terms of the independent variable. Differential equations then kind of evolve and morph, and we all of a sudden now have Diffie-Qs that are in terms of the independent and dependent variable. And the study of Diffie-Qs is how these different manifestations of differential equations lend different possible solution methodologies. So autonomous differential equations are differential equations that are exclusively in terms of the dependent variable. Sometimes there's this longing to always talk about functions or Diffie-Qs in terms of the independent variable, which is perfectly fine. The phrase the independent variable not being explicit is really just means that your differential equation here depends on the dependent variable and really not so much on the independent variable. In this case here, you can think about this as maybe a population over time. And if you think about this, the growth of a population over time, what this Diffie-Q is telling us is that the growth of a population over time has nothing to do with time at all. It has everything to do with the size of the population. Another kind of more relevant growth model that you probably could relate to more is the spread of a rumor. that the spread of a rumor actually is dependent not on the amount of time that has elapsed. The spread of a rumor, it depends on the number of people who know the rumor. And that rate of growth is, I think it's a very sharp exponential growth function. The more people know, the more quickly it spreads, right? So here is a case where we have an autonomous Diffie-Q, fairly simple one, and we're not necessarily going to solve this, though we could, I should say that. How would you go about solving this Diffie-Q if you had to? This would involve a separation of variables. And then you look at the right-hand side here, and when you get to the step where you need to integrate, hopefully you'll notice that what you're integrating here is a proper rational function. A proper rational function. And it's a proper rational function of the simplest type. Constant up high, linear factors or degree 1 factors down low. And what you could do is you can just go ahead and practice the method of integrating by partial fraction, which is the method of choice here. And, you know, maybe now's a time, why don't you stop me and just go ahead and do that and then just consult one another. You know, we're still very much in the early stages of laying down our Diffie-Q foundation. After you've done that, let's come down here. You know, I know you did slope fields and talked about slope fields last year. There's another way you can really kind of visualize solutions to Diffie-Qs, particularly ones that are autonomous. You can think about the roots of this Diffie-Q. In other words, if I look at this, at p equals 0, and at p equals 4, it appears that dp by dt equals 0. So I'm going to go over here and just do this. At p equals 0, and then at p equals 4, after all, p is the y-axis, so to speak, right? So don't lose sight of that. This is the p-axis, this is my x-axis, or my t-axis in this case. So it appears that I should have some kind of a horizontal tangent line at p equals 0 or p equals 4. And then what I'm going to do here is I'm just going to check and see, because when I have p equals 0 and p equals 4, that leaves me here with, look, these 3 intervals of p where I can determine the sign of dp by dt, right? So let's see, between 0 and 4, I'm going to pick a convenient value like 1 maybe. If p equals 1, would you agree that dp by dt is negative? Yes? If dp by dt is negative when p equals 1, or I should say this, if dp by dt is negative for any value of p between 0 and 4, that tells me then that the p function has to be decreasing. I'm just going to make a little note on my axes. That means the function should be decreasing in this interval. If I go to, say, p equals 5, dp by dt is positive for all these p values, which means the function should be increasing, okay? And then I'm going to come down here. Oh, very interesting. So for values of p less than 0, dp by dt is increasing. So let's see. Let's talk about the interval between p equals 0 and p equals 4 for a moment. And let's talk about the fact that the function we're looking at has to be decreasing for p between p equals 0 and p equals 4. And yet we know that at p equals 0, there's some kind of like horizontal, right? Horizontal tangent line, right? Because this suggests horizontal tangent line. And also there should be some kind of horizontal tangent line at p equals 4 too, right? A rough schematic here maybe looks something like this. It could be a rough schematic of what p could look like. Maybe it looks something like that. Because a horizontal tangent line, right, it could be something that the function approaches. Does that make sense? And then I'm seeing over here, let's see. So for values of p above 4, the function's increasing up here. but there's still this horizontal tangent line. So maybe this function looks something like this, right? Who knows? Because there's no other horizontal tangent line above. And then for values of p less than 0, maybe we've got something like this going on, right? So that's pretty interesting. And what's happening here is, if I think about this, I wonder if someone could ask the question like, but wait, Miss Yam, how do you know that this curve, see the curve that I drew here, how do I know it doesn't do this? Like, doesn't do this, and then like have a min at p equals 0, then go up. And my answer to that is I'm paying attention to what the function has to be doing between those y values, right? Increasing, decreasing, increasing. I think someone else could ask the question like, how do you know the curve couldn't, go like this and then like go above and then down, right? And again, it's because of the behaviors between these intervals of y. I should also say here clearly that the family of solutions to this differential equation, if I look at all of them, the aggregate here is clearly not a function of x, obviously. But if this were a diffie-q where I was given some particular point, like maybe I was told that at t equals 17, p equals 11 or something like that, then in that case, this curve, one of these curves, would then be a function of t that would be the solution. In any event, just something to show you. Some keen vocabulary, if you're into that kind of thing, is this horizontal asymptote, because this picture has two asymptotes, right? And if you look at this function from left to right, or as time elapses, this p equals 0 is called a stable asymptote. And the reason why it's a stable asymptote is because over time, the two potential curves converge upon the asymptote. P equals 4, on the other hand, you want to guess what it is? It is called an unstable asymptote. Okay, so up until now, I didn't know I don't think you ever thought of asymptotes having an adjective attached to it, let alone one that could be stable or unstable. But an unstable asymptote is one that is not converged upon by both by all the entities. Now, I should tell you this too. Even if this was a case where one curve approached the asymptote and the other one did not, I believe that is still considered an unstable asymptote, but I like to call it a partially unstable asymptote because that's really true. It's not entirely unstable, it's just partially unstable. Okay? Okay, let's take a little walk down memory lane. Why don't you come down here and look at slope fields and match them up. This is just taken straight from your calculus textbook last year. When you're doing an exercise like this and you're asked to match up diffie-q's with slope fields, you'll want to look for easily identifiable features like, what do you think? Where dy dx is horizontal, right? Looking for points of horizontal tangency. Also, similarly, looking for points of vertical tangency. Like I'm noticing here that wherever y equals 0 here, dy dx is undefined. So looking for points of horizontal tangency, looking for points of vertical tangency. Then once you do that, I like to kind of swing around and look at things like, I don't know, like looking at quadrant 1, right? Quadrant 1 are all points where x and y are positive. And in this slope field here, when x and y are both positive, dy dx is positive, and so on and so forth. Okay, so go ahead and match these up and check with someone around you and then replay me. And here are the answers that I got. What do you think? Excellent. Okay, everyone, what I'm going to do is go and post homework now on the teacher page. And I will not see you tomorrow, but you will hear me. Okay, goodbye.